The Su-75 Checkmate program is moving through a phase where Russia is trying to demonstrate that the aircraft is more than a display model and that it has progressed into substantive engineering work. Since its unveiling in 2021, the aircraft was initially seen by many observers as a concept primarily intended to attract attention and possible external investment. For the first few years, most of the information surrounding the project consisted of broad statements and appearances of mock-ups at exhibitions. These mock-ups changed slightly in design each time, indicating that engineers were still refining the overall shape, internal arrangement, and intended systems but without a working prototype at that stage. Over the past year, however, Russia has begun referring to the aircraft in language that typically corresponds to real prototype maturation. This includes descriptions of system integration, internal testing procedures, and preparation activities that commonly precede initial ground running of engines and avionics. When a manufacturer begins discussing things such as electrical system checks, power distribution tests, sensor calibration, and physical integration of the engine into the airframe, it usually indicates that the aircraft has been built to a degree where engineers can conduct combined systems verification. Modern combat aircraft rely heavily on the harmony between structural design, flight computers, propulsion units, hydraulic networks, and software. Each component must be tested individually and then tested again once connected together. Engineers must ensure that the aircraft's power supply can handle peak loads, that the flight control computers receive accurate inputs from sensors, that wiring harnesses are properly shielded, and that the aircraft can safely undergo the mechanical stresses associated with engine startup and fuel flow. The repeated announcements pointing toward a 2026 first flight indicate that the program leadership believes the aircraft is close enough to attempt the sequence of steps leading up to takeoff. It is important to understand that a first flight target is not a casual statement. It implies that major structural components have passed basic stress evaluations and that the critical systems, flight controls, electronics, hydraulics, and engine, are installed or nearing installation. Depending on the timeline, engineers might already be preparing for the first engine run. Before an aircraft can reach that point, they must test fuel lines for leaks, confirm fluid pressures in hydraulic actuators, validate the cooling system, and check that the onboard computers correctly interpret thousands of signals flowing through the aircraft. Only when these preliminary steps are completed does the aircraft move to the phase where the engine is ignited while still secured to the ground. The Su-75 program also continues to project the idea of an unmanned companion version. This version is referenced by Russian officials as part of a family of aircraft based on the same core design. The unmanned model has been displayed as a mock-up with subtle structural differences, such as altered fuselage shaping and areas likely intended for additional internal payload or greater endurance. Russian industry presents this unmanned variant as a way to extend mission flexibility, allowing the aircraft to perform tasks without exposing a pilot to risk. The concept fits with broader aerospace trends in which nations look for ways to supplement manned fighters with unmanned aircraft that can accompany them or conduct independent strike and reconnaissance missions. However, the unmanned version appears to be at a far earlier stage than the manned version. The lack of discussion about specific guidance systems, autonomous flight algorithms, communication links, or mission control architecture suggests that the unmanned model remains a theoretical component rather than an object undergoing engineering trials. Transitioning from a model to a flying unmanned aircraft requires extensive work in control logic, redundancy design, safety programming, and remote command protocols. Without reference to such development steps, it is reasonable to conclude that Russia is concentrating its available resources on the manned prototype, because proving that one version can fly would strengthen the justification for later investment in the unmanned variant. The Checkmate program's timeline shifts are an important part of understanding its current state. When Russia first introduced the aircraft, it promoted an optimistic flight schedule that was not met. This is not unusual in advanced aviation projects. Early timelines often assume ideal funding and smooth engineering progress. In reality, Russia's aerospace industry has been under pressure due to economic limitations and the need to support several existing production lines. Manufacturing combat aircraft is resource-intensive, requiring specialized composites, precision machining, high-grade alloys, electronic components, and propulsion technology, all of which test a nation's industrial capacity. When multiple programs compete for the same pool of engineers and factory space, schedules tend to stretch. The fact that Russia is now describing pre-flight testing steps suggests that the project has survived earlier uncertainties and secured enough support to proceed. Moving from a mock-up to an integrated prototype is a significant internal milestone, requiring not only technical preparation but also substantial financial allocations. Engineers must commit thousands of hours to assembling the airframe, installing subsystems, and validating their operation. Each of these steps costs money, materials, and man-hours, which a country does not spend lightly on a project it does not intend to pursue further. If the first flight takes place in 2026 as Russian officials currently assert, that event will launch the aircraft into a prolonged test period. The first flight is usually very short and is not meant to demonstrate performance but rather to verify that the aircraft remains controllable, stable, and responsive in the most basic sense. Test pilots typically keep landing gear extended, maintain low speeds, and avoid sudden maneuvers. After this flight, engineers examine flight data, inspect the airframe for early signs of stress, and make necessary adjustments. Later flights gradually explore higher speeds, increased altitudes, tighter turns, and more complex maneuvers. Only after many successful flights does the aircraft begin to test advanced avionics, simulated weapons loads, and aerodynamic behavior in different configurations. For the Su-75, a successful test program will depend not only on good flight performance but also on the reliability of the onboard electronics and software. Modern fighter jets rely heavily on digital systems for stability control, radar operation, threat detection, communications, and targeting. Any software instability can ground the aircraft for extended periods. Creating a functional, reliable integrated avionics suite is one of the most challenging aspects of modern aircraft development, often taking years of refinement. The manufacturer will also need to balance aerodynamic efficiency with thermal and structural requirements related to stealth shaping, internal weapon carriage, and material durability. Another challenge lies in sustaining the program through its test phase. Countries sometimes complete a prototype and achieve first flight but then slow down or suspend development due to cost overruns or shifting priorities. For the Su-75 to progress beyond this stage, Russia must maintain steady investment in test flights, data analysis, redesign work, component upgrades, and manufacturing infrastructure. Each of these requires stable industrial support. If Russia wishes to pursue export sales, it must also demonstrate reliability, maintainability, and a clear production plan. Customers typically seek assurances that supply chains, spare parts, and training systems will exist for decades. The current moment in the Su-75 program is therefore one in which Russia is attempting to transition from conceptual promotion to demonstrable progress. The repeated references to system integration and the insistence on a 2026 first flight show that the project has moved forward enough to suggest concrete engineering activity. At the same time, the program faces substantial hurdles: the technical demands of modern aircraft development, the financial strain of running multiple military aviation projects simultaneously, and the need to convince potential buyers that the aircraft will actually reach mass production. The unmanned variant adds both ambition and complexity. While it enhances the project's appeal by suggesting adaptability, it also introduces a parallel development path that may be difficult to support without significant additional resources. If the manned prototype succeeds in flight testing, work on the unmanned version may accelerate. If difficulties arise, the unmanned version may remain conceptual for an extended period. The Su-75 program stands at a pivotal stage. Russia has moved beyond the phase where the aircraft was an abstract idea and has begun taking steps that indicate the existence of a real prototype. The year 2026 is positioned as the moment when the aircraft could first leave the ground, which would be a decisive technical milestone even though it would not signify readiness for operational service. Whether the project advances rapidly, slowly, or unevenly will depend on Russia's ability to sustain the engineering, financial, and industrial commitment required by a next-generation combat aircraft.